Hi, in this video I'm going to talk about permeability and how it is related to the porous media properties. And this is a part of our bachelor level course on groundwater hydrology. Okay, so as discussed in the previous lecture, many people have been trying to relate the permeability to the porous media properties. And Cosney was one of the first to invoke the analogy between the Darcy's law and Poiseuille's law to relate the permeability to the porous media properties. Okay, so here you have Poiseuille's law, that is R squared divided by 8 mu times delta P over L. Okay, so this is the Poiseuille law that is used to describe fluid flow velocity flowing through cylindrical tubes. We had this in one of the previous lectures, okay? And you multiply that by epsilon, that is the porosity of the porous media, because the fluid can flow only through the porous spaces. So you multiply that by the porosity, and then you equate it with the Darcy's law, that is K divided by mu times delta P over L, okay? So delta P over L by delta P over L is out here, and you can rearrange the remaining as K is equal to epsilon divided by 2 times R divided by 2 with the power of 2. Okay, R divided by 2 is called hydraulic radius, that represented by RH, and thus the more general form of the Cosney's model can be written as K equal to epsilon porosity times RH with the power of 2. Instead of R divided by 2, I put RH here, divided by C, and the C is the shape factor. And in the case of cylindrical tube, it is equal to 2, okay? And so in terms of the definition of the RH, that is the hydraulic radius, for porous media, there is an equation that can be used to calculate RH, that is equal to epsilon divided by AV, that is a specific surface area, times 1 minus epsilon, okay, 1 minus porosity. And if you plug this expression into this equation, okay, you can rewrite the permeability as epsilon times RH with the power of 2, that will be epsilon with the power of 2 times epsilon will be epsilon 3, divided by the AV with the power of 2 times 1 minus epsilon with the power of 2, and everything should be multiplied by this shape factor. Okay, so the permeability will be equal to epsilon with the power of 3 divided by C AV with the power of 2 times 1 minus epsilon with the power of 2. And this model was extended by Carmen, 1939, by adding flow path lengths called tortuosity, basically, tau, represented by a parameter tau. Okay, so basically, let me first explain what is tortuosity. This is a very basic explanation of tortuosity, and I'm sure you can find many more information on that. That is defined, basic tortuosity is defined as the ratio of average path of flowing fluid, okay, that is this dashed line, for example, that is the path that the flowing fluid is taking, divided by the ratio of that and the shortest flow path, here L. Okay, so the idea here is that because of the presence of these solid particles, the fluid basically the fluid goes through a complicated pathways to get out of the medium or to flow through the medium, right? And that affects the permeability. Okay, and tortuosity is often greater than 1 and may exceed as well 2, and also it tends to increase with the reduction of the porosity. Here, this figure, let me move this one. This figure here, that is the tortuosity for different material or different boundary condition as a function of the porosity. As you can see, when the porosity is equal to 1, the tortuosity is 1, because there is no solid grains there. That when the porosity is 1, that means it's empty space. That means there is no solid grains there to make a tortuous pathways for the fluid. And when the porosity decreases, as you can see, the tortuosity tends to increase. Okay, and that affects the permeability of your media. So get back now. We go back. We get back to the previous slide. And so here we had the equation. So Carmen in 1939 added this tortuosity parameter to this definition. So therefore, K permeability is equal to epsilon with the power of 3 divided by C. He added this tau here, tau 2 times AV with the power of 2 times 1 minus epsilon with the power of 2. Okay. We discussed already about the tortuosity. So now in many cases, the parameter, the factor C tau 2 is roughly equal to 5 because C, the shape factor, is around 2 to 3 and tau, the tortuosity, is between 1 to 2. Therefore, C tau 2 is roughly around 5. Okay, so this is like a constant around 5. And then the AV, the specific surface area, for a spherical particle is equal to 6 divided by d. We derived that in one of our previous lectures. Okay, so in this equation, if instead of C tau 2 you put 5, and if instead of AV you put 6 divided by d, and then you can rewrite this equation as permeability equal to d with the power of 2 times epsilon with the power of 3 porosity divided by 180 times 1 minus epsilon with the power of 2. Okay, with the d is the equivalent particle diameter. Okay, here you have to pay attention that this equation works well when you can assume, or when the medium under consideration consists of particles of roughly a spherical shape. Okay, why is that? Because AV, instead of AV, we wrote 6 divided by D, and that is valid when you're dealing with the spherical particle. Okay, so using this equation now, you can see you relate the permeability to the particle diameter and the porosity of the porous media. Okay, so here there's a table just to show you some typical values of permeability in different units. So here the small k is permeability and the capital K is the hydraulic conductivity in different units. You can also as well see that based on the unit, because the hydraulic conductivity, as we discussed in the previous lecture, has the unit of velocity basically, so centimeter per second or meter per second, while permeability has the unit of length squared, the dimension of length squared. Okay, and Darcy is the unit of permeability. Okay, and then here this part is for the rock, and this is for the unconsolidated deposits like sand and gravel and silty sand and so on. What is interesting here to highlight is that this wide range of variation of the permeability, and as you can see, it changes, hydraulic conductivity or permeability changes like 13 orders of magnitudes, because from, I don't know, 10 to the power of 2, if expressed in the unit of centimeter per second, to 10 to the minus 11. So 13 orders of magnitude. And that which makes this parameter, this property, a very, makes it highly nonlinear property. By a little bit of change of the boundary condition, the permeability can change orders of magnitude, and which makes it very important to have a accurate understanding of the permeability of your domain to be able to describe the subsequent flow and transport processes. Okay, and that was it for about the permeability and hydraulic conductivity and how to relate the permeability to the transport properties of porous media. I hope you found this video helpful. Thank you.